This is Team 3 for cost optimization for a data center. This includes Amr, Hunter, Lena, Sam, Sanket, Tyler. The chosen system for this project is to power a 10 megawatt non-grid connected data center. The three subsystems that we will be analyzing are energy generation, energy storage, and thermal management. Assumptions will be discussed throughout each subsystem. The system model can be seen on the right, and all three subsystems had an output of cost. The shared inputs are macroeconomics. The coupled output variable is cost. The linking variables are energy output, waste heat, state of charge, and thermal management power demand. Objective function is determine the minimum cost for energy generation for a constant load of 10 megawatts. The design variables are the number of each type of energy generation source. The constraints are 0 to infinity for each energy source and the max power of 87,600 megawatt hour and renewables less than 40% of the power. All data was taken from EIA. Intermediate variables were the cost of each energy generation type, and the costs were broken down into capital cost, fixed O&M cost, and variable O&M costs.
The modeling approach used was to sum the cost of each of the energy generation types and find the minimum of that. The assumptions we used were that the cost is assumed over 10 years. The max wind and solar energy is 40%, the constant load of 10 megawatts, and we could only use the standard size solar array, wind turbines, natural gas combined cycle, and coal turbines that were found in the US EIA outline from January of 24. And the major modeling steps are outlined below. A GA function was used to find the optimal cost using MATLAB, which was run 5 times. MATLAB and a GA function were used because of its accessibility through the optimization toolbox. The results for the 5 iterations can now be seen on screen with different initial values used for each of the 5 iterations. The lowest cost output was 0 solar arrays, 0 wind turbines, 16 natural gas turbines, and 0 coal turbines. And this resulted in about 13.7 million. As mentioned, the cheapest result was just natural gas turbines with a total of 16. In the 5 different runs, 5 different solutions were obtained. All solutions, however, were within 5% of that minimum value obtained. The solutions did have very different energy generation compositions. The optimal solution had 0 renewable energy generation, but for 5% more cost, the energy generation was over 18% renewable. So this shows us just how important policy can be in the energy sector.
Energy storage subsystem ensures that the power demand is met at all the time. The objective function is generated considering various costs involved like capex, operation, and degradation with a goal to minimize the overall cost. The 3 main variables are used to compute the cost minimization and yet meet the load demand: battery energy capacity, battery power capacity, and the minimum and maximum SOC. Key constraints include usable energy should be greater than or equal to the required energy. Bounds are defined for charging and discharging limits and keeping the energy and power limits within rational bounds. 3 mathematical models used are SOC, energy capacity, and power capacity. Extremely low SOC indicates storage may not be able to support the load. Extremely high SOC indicates storage may not be able to access generation. Energy capacity model dictates how long the demand can be met without generation. This includes fixed data center load, required backup duration, discharge efficiency. Defined power capacity model assumes a constant load requirement ignoring transient or dynamic events.
Building on the design variables and constraints previously defined, we evaluated the total battery cost and used a generic algorithm to search the design space for the minimal cost solution. The optimization assumes lithium-ion battery costs, power electronics cost, constant discharge efficiency, and a fixed 4-hour backup duration. The modeling process follows these steps: formulate the objective function, run the optimization, and validate the results. For the optimization method, we used a generic algorithm in MATLAB to find the optimal battery design. The algorithm generates different candidate solutions for the battery size and evaluates their total cost while checking that all system constraints are satisfied. Over several iterations, the algorithm improves the solution and converges to the design that minimizes cost while still meeting the required power and backup energy demand.
Multiple iterations were performed to understand the impact of variables and bounds. Iteration 1 provides decent costing from a mathematical point, but physically it won't make sense as the allowable battery discharge is 1%. Iteration 3 gives the least cost but fails the fundamental condition of available energy is less than the required energy. Iteration 5 provides close to optimal solution but uses slightly higher energy capacity. Iteration 2 is the optimal costing solution with logical SOC range and energy and power capacity.
The optimization results suggest an optimal battery energy capacity of about 54.7 megawatt hours with a power capacity of 10 milliwatts and an operating SOC range from 0.15 to 0.9. This gives about 42.55 milliwatt hours of usable energy, which matches the required backup energy for the system. As a result, the battery can provide approximately 4.26 hours of full load backup. At the optimal solution, the active are the energy availability constraint, the power capability constraint, and the SOC operating limits. The total estimated storage system cost is about 8.14 million.
For subsystem 3, the thermal management system, the parameters are the heat input and the fluid properties. The design variables are table indices for tube geometry and shell geometry, the number of tubes, and the tube length. The constraints include lower bounds on the thermal duty, effective temperature delta, and Reynolds number, upper bounds on the outlet temperatures, pressure deltas, and tube bundle spacing, as well as upper and lower bounds on the number and length of the tubes. The objective function for this subsystem is to minimize the costs of construction and operation. For this subsystem, MATLAB was the selected software, and a MINLP approach was used due to 3 of 4 design parameters being integers. Within MATLAB, the genetic algorithm was used as the solver methodology. The assumptions made will be covered on the next slide, and the major modeling steps are as shown. The assumptions for our model include the cost per area of heat exchanger material, that the type of heat exchanger being used is a shell and tube, that the fluid being cooled is water, and the cost of using on-site power as opposed to grid power. From the other two subsystems, we can arrive at initial assumptions for the heat input to the system due to worst-case operation, and what the hot side fluid inlet and outlet temperatures can be based on operating ranges.
After running the algorithm 5 different times, varying the starting values of the design parameters each time, the total cost of the heat exchanger was shown over a 10-year period to be $145,976, with 98.3% of that coming from the capital costs and the other 1.7% being operational cost. The resulting cost-optimized heat exchanger can be described here. We found that no matter what our input parameters were, we found the same deterministic solution would come out of our runs. There are only 3 active constraints in use for those optimized solutions. The hot side maximum output temperature, which is driven by generation and storage's cooling medium requirements, the tube bundle being able to actively fit into the shell, and the minimum diameter available for the tubes as they were drawn toward smaller tubes overall.